Yeah. See, before I would like to show you a connect with Anova. If you have an exposure with Anova, analysis of variance, you can link Anova to the regressor context. I just tell you the Anova and the context of linear regressor. There is an interesting connect. You're familiar with Anova, analysis of variance, what we do in analysis of variance. We try to say this is a box plot representation of three different means. I have represented like this. This is one mean and this is another mean. Three groups. So x1 bar, this is x2 bar, and this is x3 bar. In Anova, what is null hypothesis? X1 bar is equal to x2 bar is equal to x3 bar. Alternate hypothesis. At least one pair means are not equal, where the whole alternate hypothesis holds good. In analysis of variance, what we try to find out, F statistic, right? F stat. What is the F statistic score? Mean square treatment by mean square error. Actually, this numerator term, it is going to calculate between sample variability. That means how each mean away from the overall mean of the three groups. It could be any continuous variable. Assume it could be any continuous variable. Say, for example, a glucose. Okay, glucose with respect to three category, I have grouped this. Say this is the diet plan 1, diet plan 2, and diet plan 3. What we are constructing? We are constructing a regressor problem, isn't it? We are constructing a regressor problem. Now we are talking to the context of independent variable, which is categorical in nature. So far, the example I have taken continuous variable. For continuous variable, we have seen the scatter plot like this, isn't it? The relationship between x and y are like this. But for a categorical variable, x is three categories. One of the independent variable is three categories. Diet plan 1, diet plan 2, diet plan 3. How each category affects the blood glucose, I wanted to investigate. In that perspective, if you look at your regressor problem, like an Anova study, what your Anova is going to tell you, in order the alternate hypothesis holds good, okay, then only I can use this diet plan as one of the feature in my model, right? If the null hypothesis holds good, imagine a situation if all three means are equal. Okay, imagine we call this a box plot. If your box plot looks like this, all three category, the mean value is more or less same. Suppose your null hypothesis satisfies. This is x2 bar, x3 bar. So irrespective of the diet plan, okay, your mean glucose is same for all three category. It is a useless feature, right? It is a useless feature. I cannot use this feature to predict the blood glucose. If there is a significant difference, then I can say that I can reject the null hypothesis. We can say that. So for that, we should get a p-value. Suppose the probability of null hypothesis being true should be less than 0.05. Okay, for 95% confidence interval, for 5% error, what is the p-value? If the p-value less than 0.05, we reject the null hypothesis, alternate hypothesis holds good. When? For that, the mean should be significant difference. Okay, there should be a significant difference in the mean. Something like this. This is another mean, and this is another mean. Is like this. So x2 bar, x3 bar. So what your F statistics is going to compute. So the larger the F statistics, to have a larger the F statistics, smaller the p-value. That means what? In order to F statistics to be the larger, my numerator should be large and my denominator should be small, isn't it? What numerator talks about between sample variability. So put together all three groups, I have a global mean. Say for my global mean is X, say it's a X bar bar. What is my mean square treatment formula? Goes like this. Okay, number of records in each group. Okay, let me use the index I for the group number. Okay, so number of record in each group, mean of each group subtracted from the global mean whole square plus, okay, say this is the number of records in group 1, number of record in group 2, x2 bar minus x bar bar the whole square plus number of record in group 3, x3 bar minus x bar bar the whole square. This is the numerator term, whole divided by, okay, k minus 1, which is degrees of freedom, is 3 group minus 1, 2. So if each mean is away from the global mean, naturally the means are far away, right? So your MSTR also goes large. What is the denominator talks about? Mean square error. The denominator talks about within sample variability. So your within sample variability, what is the spread of each group? What is the spread of each group? Imagine if the spread is larger spread, what will happen? No, one group will try to overlap with another group.
Normal function is 0.
So a large numerator with a small denominator will make your F statistic score larger. So larger the F statistic score, okay, you have a high chances of rejecting the null hypothesis. Your alternate hypothesis holds good. That is what Anova does. Additionally, what linear regressor is going to do, your Anova just tells that how significant your means are different, right? Whereas your regressor model is going to capture the difference in the form of a slope. Capture the difference in the form of a slope. I just give you an example for it. Okay, how regressor model handles a categorical variable. First, let me explain this with 2 category, then I'll take you to the 3 category. Same the glucose. Suppose I have 2 category. This is one category called exercise category. Okay, this is another category, no exercise. No exercise. So in my data frame, okay, data frame is nothing but your tabular data structure. You have so many features. What is the variable you are going to predict? Glucose. GLE. This is a OE variable. Already we have investigated continuous variable like a body mass index, weight, height, how it affects the blood glucose. Okay, now you are investigating one of the categorical variable, whether the person is doing exercise or no exercise. This is a 2 category. Okay, so let me label the exercise category as label 0, no exercise category as a label 1. The mean glucose value of the exercise doing people is, say for example, 120 milligrams. The mean glucose of no exercise people is 180 milligrams. Actually, for the 2 group, suppose if you wanted to formulate hypothesis testing, it comes under 2 sample t test, isn't it? X1 bar is equal to x2 bar, alternate hypothesis x1 bar not equal to x2 bar. So null hypothesis to be rejected, the p-value should be less than 0.05, so that alternate hypothesis holds good. If there is a significant difference in the 2 mean value, okay, HA holds good. So then that feature is a useful feature. If the 2 means are same, that is a useless feature, isn't it? I don't include that feature into my model. So remember, the linear model requires a statistically significant. To be a statistically significant, it should pass the statistical test. So how linear regressor model is capturing this difference? Okay, your linear regressor model try to fit this time. It has to fit a slope for a categorical variable. So y cap is equivalent to beta naught plus beta 1 x. This time, what is your x? Exercise or no exercise? Okay. So your exercise habit is your independent variable. Exercise or no exercise. So whenever I substitute 0, it is exercise, right? Exercise. So when my input goes 0, my model would predict this category glucose. That means my beta naught I can take 120. Whenever I move from this category to this category, when I substitute 1, I'm saying it is a no exercise category. Presence of no exercise, 0 means absence of no exercise. That is how regressor model understand the label 1 and 0. Please understand 0 and 1 are nominal quantity, does not carry any weightage, just a nominal quantity. Whenever I present 1, it should increase the slope from 120 to 40, sorry, 60. So 120 plus 60, you got 180, right? So this is actually your model equation goes like this. So 120 plus 60x. You substitute x equal to 0, what happens? It predicts 120, which is the exercise category. When you substitute x equal to 1, 120 plus 60, 180, it predicts this category. So class-wise mean value, your regressor model will predict class-wise mean. That's all it will do for a categorical variable. Suppose you reverse the label, what will happen? If I reverse the label, okay, your equation becomes a negative slope you'll get. That's all the changes. So now I have labeled exercise as 0, no exercise as label 1. Suppose if I reverse the label, what will happen? Exercise, so this plot I can modify like this. So this time you wanted to label, okay, no exercise, you wanted to label 0. Okay, earlier you have labeled the no exercise as 1. This time the no exercise, which is the mean value, which is 180, you wanted to label as 0. And exercise category, you would like to label it as a 1. Okay, 1 is exercise, this is no exercise. So this mean is 120. This time your linear regressor model will learn this pattern. The equation goes like this: 180 minus 60x. GLU cap equivalent to 180 minus 60x. Early it is 120 plus 60x. This time it is a 180 minus 60x. When you substitute 0, what happened? No exercise. When it is a no exercise, the average blood glucose is 180. Whenever you substitute 1 for x, it is 180 minus 6. Okay, your exercise, 180 minus 60, 120. So this is how your regressor model handles the categorical variable. There's no issues for 2 category, right? Actually, the problem comes with more than 2 category. Imagine a situation, I have 3 category. Like the Anova test. We talks about Anova, right? So in order the 3 means has to be statistically significant. Okay, it should pass the statistical Anova test. To confirm, yes, the means are significantly different. This mean is, say, for example, this is 100 milligrams. This mean is 130 milligrams. Okay, this mean is 180 milligrams. Okay, this time maybe I labeled this category as label 0. This category is label 1. This category is label 2. Any order you can label, it doesn't matter. Your label does not matter. But I should use this label as a nominal. Okay, if I directly use the equation beta naught plus beta 1 x for this, assume when I substitute x equal to 0, okay, I'm saying my model should predict 130. Okay, in that case, beta naught you fix 130. Okay, whenever you substitute x equal to 0, your intercept is 130. It works for this category. And whenever you move from the 0 category to category 1, you substitute from 130, there is an increase in the slope, 50. So you fix 50 is the slope. But when you substitute this category 2, when you substitute 2, what will happen? 130 plus 50 times 2, 130 plus 100, it is going to give 230. But for this category, my model should predict 100, right? So keeping the label like this will not work for the linear regressor. So what we represent, we used to represent this data as a one-hot encoded vector. One-hot encoded. Or there is one more terminology in the data science. We call it as a dummy encoding. Dummy encoding. What is this? So I create a dummy encoding, okay, for two categories. For example, for these two categories, dummy encoding for category 1, dummy encoding for category 2. Okay, whenever I have category 1, this is a category 1 diet plan. Assume they have 3 diet plan. Okay, diet plan. Category 1 diet plan, I represent my record with a 2 column. Number of category minus 1. You have 3 categories, so 3 minus 1 dummy encoding. If I have 4 category, 4 minus 1, 3 column I should set. Whenever I have a diet plan 2 is represented as absence of diet plan 1, present of diet plan 2. Whenever I have a diet plan 0 label, I would say neither this nor this. That is why always the number of category minus 1. So I have 3 category, I created a 2 dummy column like this. So 0, 0 means model will understand it is a neither this diet plan nor this diet plan, something a third category. 0, 1 means it will understand diet plan 2. 1, 0 means it is a diet plan 1. This is a dummy encoding. Now your regressor model try to understand, learn this category like this manner. So GLU equivalent to beta naught plus beta 1 dummy encoded 1, beta 2 dummy encoding 2. So whenever 0, 0 means, okay, 0, 0 means it is a present of diet plan 0 category. What model should predict 130? So easily you fix beta naught is 130 for beta naught. So for diet plan 1, 10, diet plan 1, what is the blood glucose level? Average is 180. So from 130, my beta 1 should be 50. Because when you plug in 10, this is cancelled, right? So 130 plus 50, it will yield 180 correctly. So how do you represent diet plan 2? Diet plan 2 is represented as a 0, 1. So when you substitute 0 and 1, this term will vanish. Okay, already fixed this beta 1 as 50 times of 0 will vanish. So what value of beta will take this 130 to 100? So it will take a negative slope of minus 30, which will make this beta not intercept to 100. So my model parameters are 130 plus 50 minus 30 or the slopes. It will work for all 3 combinations. 0, 0, you substitute, what happens? 130. Whenever I substitute 10, 130 plus 50 times of 1 plus 0. So 130 plus 50, it becomes 180, works. Whenever finally you substitute 0, 1 combination, 130 plus 0 minus 30, it becomes 100. So this equation, so this is your final equation, 130 plus 50 times dummy 1 minus 30 times dummy 2. This is how your model will learn a dummy category, the diet plan. If it is a 2 category, there is no need to create a dummy encoding because your 2 minus 1 is a single column, right? Single column. So single column means it's the present of exercise, absence of an exercise. 1, 0. 1 means the present of exercise, 0 means absence of exercise. Whenever you have more than 2 category, we have to create a dummy column like this, and we can solve this problem like this. So the point here is 0, 1, 2 should be considered as a nominal data. Nominal scale means the number does not carry any weightage. It is just it belongs to that category. That's all. Since it's being labeled as 0, 1, 2, I have to make it as a model will understand like this. Model will learn like this, rather understanding label 2 does not carry any weightage. So this is the way model learns for the categorical variable. So I'm associating Anova with respect to the linear regressor. Anova just tells the means are significantly different. How much they are different, your regressor model captures the difference in the form of a slope. Additionally, it captures the slope information. So that is the link between Anova and a linear regressor. So now I'm going to demonstrate a gradient descent, a numerical example to appreciate what we have discussed just before break. Hope you're able to see my slide. This is visible, right? So look at the Anova definition. You know that Anova definition is a statistical model that we use to predict a continuous outcome. See, so we consider Anova as a regressor with a dummy variable, that is a regressor with a categorical variable. So in Anova, we compute this mean square treatment and mean square error within sample variability, and between sample variability, we take the ratio, and the larger the fraction, your Anova table look like this, isn't it? So the larger the F statistics score, naturally, I tend to reject the null hypothesis. Whereas your regressor model additionally captures the slope information. So how much difference? Anova just tells, are they statistically different? Additionally, the regressor model going to capture the difference in the form of a slope. So that is a connection. Your linear regressor can be interpreted as a Anova. So all these definitions we have seen about the linear regressor model. Now I'll take you directly to the numerical example and a quick overview of a linear gradient descent algorithm, what we just discussed. We started with the cost function. This is a cost function. We calculate the error gradient minus of y minus y cap for dou beta naught. Similarly, dou beta 1 minus of y minus y cap times x. This derivation we have seen. Okay, let us appreciate the gradient descent with a numerical example. One small toy example I have taken. Okay, when x is 2, y takes 5. When x is 5, y takes 12. When x is 7, y should take 15. Okay, as you see that as x increases, y also increases. So it is a positive correlation. So what I'm going to do, I'm going to start with some random initialization for beta naught and beta 1. So beta naught I have taken randomly 1 and slope I have taken randomly 3. Okay, just I have taken randomly. Okay, and for this process I have assumed learning rate as 0.01. Okay, to solve this numerical exercise I have taken 0.01. So you know this formula. What is the updated slope or updated intercept is given by your initial beta naught minus eta times of this gradient term, dou SSE by dou beta naught. To update the slope, I should substitute dou SSE by dou beta 1. At what rate I should adjust my slope so that I can minimize the error. Okay, that is the logic here. So for the randomly initialized slope and intercept, so I compute my equation. 1 plus 3x is the equation. Okay, you substitute x is 2 here. You just plug in 2. 2 3s are 6. 6 plus 1 7. Then you plug in 5 here. 15 plus 1 16. Then you plug in 7 here. 21 plus 1 22. So you computed the y cap. Okay. Now I need to compute my SSE, sum square error. You know that SSE is being defined as 1 by 2 times y minus y cap the whole square. This 1 by 2 is introduced just for the mathematical convenience, because when we derivate this 2 and this 2 should cancel. For that purpose, this 1 by 2 is being introduced. Many literatures, they have simply kept that scaling factor 2 times of y minus y cap without introducing this 1 by 2. That is also equivalently correct. So according to this formula, when I substitute y minus y cap, 5 minus 7, which is minus 2 whole square, 4 scaled by 1 by 2, 4 by 2, 2. 12 minus 16, minus 4 square, 16 by 2, 8. 15 minus 22, minus 7 whole square, 49 by 2, 24.5. My total SSE is 34.5. Initially, my cost function for the random initialization, my cost function is somewhere at high score 34.5. My scope is to minimize this error, right? For that, I need to apply this formula, delta beta naught, delta beta 1. I'm using the formula minus of y minus y cap, minus of y minus y cap times x. Just now we have derived this. So 5 minus 7 minus 2 minus of minus 2 become plus 2. Similarly, individual differences I calculate. This is my total gradient. Similarly, this is the total gradient for slope. This is the total gradient for the intercept. Okay. So now I'm going to substitute this 13 and 73 in the formula. Look at this, 13 and 73 in the formula to calculate the updated intercept and updated slope. My initial intercept is 1. So 1 minus Learning rate 0.01 we have taken for this example times 13. What is 13? 13 is the total error gradient for to update the intercept. Similarly, whenever to update the slope, I should substitute 73. My initial intercept is 1. After update, it becomes 0.87. My initial slope is 3. After updating, it is 2.27. So with the updated slope and intercept, I frame the equation now. This time, my initial earlier it is my equation is 1 plus 3x. Now the equation is 0.87 plus 2.27 times x. Okay. Now with the updated equation, you recompute your y cap value, plug in your x value now. This time 2 times 2.27 plus 0.87, you got 5.41. 2.27 times 5 plus 0.87, you got this y cap value. Compare the initial y, the predicted value with the random initialization. Actual y is 5, but model predicted 7. Even with one iteration, even with one update, what happened within one epoch or one iteration? Earlier model predicted 7. This time model predict 5.41, which is pretty close to the 5. Now can you see even with one adjustment, my y cap value is approaching to the actual y. The actual is 12. This time model predicts 12.22, but with the random initialization, actual is 12. My model predicted 16. Bit far away. Now it come closer to the actual 12.22. Earlier 15 in model predict 22. This time 15 is being predicted as 16.76, pretty closer. Now if I compute the total SSE, initially you can see the total SSE is 34.5 units. Now my total SSE came down drastically to 1.65 unit. See, from 34.5 there is a drastic reduction to 1.65. My individual gradient also, you can see initially my total gradient for intercept is 13 and the total gradient for the slope is 73. This score also reduced to 2.39, 14.24. Now I need to adjust this value using this gradient 2.39 and 14.24. So using 2.39 and 14.24, I adjust my intercept and slope again. Now my intercept got adjusted to 0.87 to 0.846. My slope 2.27 got adjusted to 2.12. But comparatively, you can see with the first iteration, there is a 1 is being adjusted to 0.87 and 3 is being adjusted to 2.27. There is a lot of difference because my gradient was very high, 13 and 73. As the gradient also decreases, error gradient also decreases. That means we are approaching to the destination. That is an indication. As the error gradient decreases, that means we are approaching to the optimal value. Since we are approaching towards the optimal value, because our predicted y is coming closer to the actual y, right? That means we are reaching the destination. That is the reason your total gradient score also decreases. As the gradient decreases, the changes in the slope and changes in the intercept value also, that difference also minimizes. From 0.87 is just adjusted to 0.846. 2.27 is adjusted to 2.12. So now I recompute my y cap. Compared to the previous iteration, look at this 5.41. The next iteration, it comes pretty closer to the 5.10. Still, it's closer to 5. So my overall SSE, can you see the earlier iteration, my overall SSE score is 1.65. This time it becomes 0.4133. Isn't it? So my overall SSE score coming down. So it's basically what you can see is what your error is getting converged. I just manually did 3 iteration. Maybe you can extend it for one more iteration if you see that the changes in the slope and intercept is very minimal. That means what is the indication for your convergence indication that your cost function, there is no further reduction. There is no further reduction or it becomes saturate at one point. So that is an indication for the convergence. So with 2 consecutive iterations, okay, your 2 consecutive iterations, there is no further reduction in your SSE score, okay, or your SSE score becomes saturate. There is no further update. There is no significant changes in the slope and intercept that happens. What happened? Initially, your SSE score was somewhere 34.5. Okay, then with one iteration reduced to 1.65. Then it reduces to 0.45 something. 2 consecutive iterations, there is no further reduction. Almost if this gets saturated, there is it started increasing. That means opposite direction started increasing. You keep on adjusting. See what happens, no? If you keep on adjusting the slope and intercept at one point of time, what will happen? No? You'll be moving your line in the opposite direction. What will happen? No? Initially, start with some random point. Then you adjust this. You're adjusting this slope and intercept. And you reaches the optimal point. This is the optimal point, right? This is you got the minimal. And still further, you keep on adjusting. Further, imagine if you keep on adjusting in a wrong direction like this, again your error increases, isn't it? Your error increases. The wrong direction if it increases, it opposite direction increases. So your convergence is 2 consecutive iterations. There is no further update in your slope or intercept. That is a convergence has happened. Your gradient descent algorithm will finally throw the best slope and intercept to us. So that is a converged score for us. So what we call this is a classical gradient descent, or sometimes people call this a full batch gradient descent. This is called as a full batch gradient descent. In recent times, people have developed something called stochastic gradient descent. Actually, it was there many years before, but people started adapting this for the deep learning, including even for the deep learning algorithms. In stochastic gradient descent, what happens? Here in classical gradient descent or full batch gradient descent, what I have done is I just substituted the summation of delta beta naught and summation of delta beta 1 in the formula, isn't it? My initial intercept minus learning rate times what we have substituted, the summation of delta beta naught we substituted. Whereas in the stochastic gradient descent, you are going to substitute one single gradient value. What do you mean by that is record by record, we are going to adjust the slope and intercept. That is the difference. Whereas in the classical gradient descent, we expose all 3 records to the model. We compute the total gradient. We have computed the total gradient like 13 and 73. Then we use that 13 and 73 in the formula to adjust the slope and intercept. Whereas in the stochastic gradient descent, first I present my one record. Initially, I start with the same random initialization 1 and 3. 1 and 3. Okay. Now, as per the equation 1 plus 3 times of x, I calculate y cap. These are the individual gradients, right? 2 and 4 are the individual gradients. Immediately, I update the slope and intercept. Can you see? My slope and intercept got adjusted by using the individual gradient. 2 and 4 I substitute to calculate this. Update the slope and intercept, then you present the second record. With the updated slope and intercept, I predict this y cap prediction is done here. Once again, calculate the individual gradient. Substitute 3.78, 18.9, I substitute. Record by record update, we are doing it. But here we are not doing a record by record update. Once all the training records are being exposed to the model, okay, I'm substituting the total error gradient I'm substituting, but here I'm doing an individual error gradient. For the linear model, you don't find any big difference between a classical full batch gradient descent and stochastic gradient descent. But when you extend this algorithm to the nonlinear model, you can see some difference. So the nature of the stochastic gradient descent tends to overfit your data because you are exposing record by record, you update the model parameters, means your model tends to overfit. At the same time, your full batch gradient descent tends to underfit when you substitute to the overall error gradient. So they have devised a mechanism, something called as a mini batch gradient descent. There is a compromise between a full batch gradient descent and stochastic gradient descent. What happens in a mini batch gradient descent? You divide the whole training record into multiple batches. Whatever I'm telling, this mini batch approach is applicable to nonlinear deep learning model, not for linear regressor. Since we are touching upon this topic, I'm just telling you for the nonlinear model, when you extend this, suppose imagine this is you have 1,000 training records. Okay, I divided into 10 batches. Okay, mini batches. So each batch 100 records. Okay, batch 1, batch 2, we have got 10 batches. We randomly shuffled, completely shuffled randomly you have taken. This 100 record will be exposed to the model. Model will compute delta summation of delta beta naught, okay, summation of delta beta 1 based on this 100 records. Once you expose this 100 records, then only beta naught update and beta 1 update will happen. Then I expose the next 100 records to the updated slope and intercept equation. Okay, we'll be calculating the individual gradient for these 100 records, and you calculate the summation of the total gradient for these 100 records. So your gradient score, you are calculating for every 100 records, you calculate the gradient and you substitute the summation of that 100 gradient in the formula. This is called a mini batch training. In full batch training, what happens? You calculate the total error gradient for once the whole 1000 records are being exposed to the model. The summation of delta beta naught, summation of delta beta 1 is calculated for index 1 to 1000, index 1 to 1000, because the summation you have done for 1000, the whole 1000 records, the total error gradient you substitute. This is called a full batch training. Stochastic is record by record update. That also not record. It's a time consuming process. Moreover, it tends to overfit. First record, model will update model parameters. Second record, third record, record by record. That is a stochastic. Some intermediate step is called mini batch. It will have a very good compromise between overfit and underfit. Most of the deep learning training models people use as a mini batch training. Neither is a full batch gradient descent nor stochastic gradient descent. Mini batch gradient descent is a popular mechanism for the nonlinear model. But to the context of linear model, as I told you, for a linear model, we have a smooth convergence. We don't find any big differences in the results. Okay, so we have discussed all the mathematics related to the linear regressor model, how a linear regressor model calculates the model parameters using a gradient descent rule. What is full batch gradient descent? What is stochastic gradient descent? What is mini batch? All three I have explained. Now we are going to see the implementation in Python notebook. We have another 45 minutes. We are going to see the implementation. See, when we talk about implementation, there are three popular tools globally, is very popular. Okay, I will tell you in the order of utilization: Python, R, and SAS. You know, since I'm giving so training for the data scientists who work in the industry, there are two things is needed. One, you have a sound knowledge of all the linear algebra, the basic calculus, and statistics. Okay, that is must. So whatever we have discussed, the math and statistic component, what is statistical test, why I do the statistical test to identify the significant feature, whether that feature is statistically significant to be accommodated by a linear model or not. For a non-linear model, of course, the statistical significant test is not required. Only for a linear model, that is a constraint. So your math and statistics knowledge with a proper knowledge in any one tool, at least any one tool, but across the globe, I'll tell you, 80% of the companies across the globe, Python is the most sought after language. It's a popular tool. I would say another 15 per language. Both are open source. I would say the SAS is a licensed product, is a heavy licensing fee. Academic versions are available even for a limited period of time. You can use academic version for a learning purpose, but it has its own limited time period. So after that time period, you have to purchase the license. This 5% I was talking about, this 5%, the SAS tool is used mainly by the pharmaceutical companies, pharmaceutical, clinical research, pharma industries. But the trend is slowly changing. But this is the situation 5 years before. Now the trend is changing. Earlier, the pharmaceutical companies who do the data analysis on experimentation on the new drug. Even our Covishield, Covaxin gone through this, your animal studies, then the volunteer studies, the how the they based on the data they have collected. For example, what is the antibody unit per per milliliter? For example, whenever they administered the Covishield for the animal studies or Covaxin to the animal studies, how much antibodies it is created, whether they are statistically significant or it's when compared to non-administered the vaccine, when after administered the vaccine, there is a significant difference in the mean value. All these investigations they have done using a SAS package. Early days, many the drug approval agencies, you know that Food Drug Administration, which is US, European has its own approval agency. In India has its own approval agency. They have a certain norm that unless otherwise you validate your data using a SAS package, then only FDA and other approval agencies. Early days, this was, I was talking about 1 decade before, around 2010, 12 and all. Around 2014, 15, these approval agencies has relaxed the norms. There's no hard and fast rule that you should use only SAS. You can even use Python and R language also. So in recent years, what I have observed in recent years, many pharmaceutical industries started adapting to the R software also. In recent years, last 3-4 years, I have seen the trend is increasing because many companies, they could not afford the very heavy licensing fee of SAS. The corporate fee is very high. Yearly, you have to renew the license. Your early renewal fee alone, it will come to many crores, 30-40 crores, in which many companies, they could not afford it. That is why they started moving to the R and Python. They started looking for the other options. Other than the clinical research and pharmaceutical domain, the remaining other domains I'm talking about e-commerce, retail, banking, finance, food industry, food processing and agricultural industry, all other industries are using Python extensively, including computer vision application, time series applications. They uses extensively this. So even for the demonstration, I'm going to use a Python tool. Okay, Python tool only I'm going to use it. There are 2 ways you can use the Python softwares. Few of you may have already exposed to Python, and many of you may not be exposed to Python software. No issues. If you're your first time user, Python user, one is a standalone installation. You just go to python.org. If you go to python.org, I will show you. You can download the latest version. See, early days we have 2 version and 3 version. Okay. Now the 3 version is more stable. If you are a first time, now only you're going to learn Python, means you can directly learn Python 3 version. But we people initially we worked on Python 2 version, then we migrated to Python 3. Past 15 years we are working on the Python because early days we work on Python 2 version. Now we migrated to 3. But to be frank, Python 2 and Python 3 version, hardly there is only 5 to 10% difference. So if you are a first time learner for the Python, I advise you directly you can learn Python 3 version itself. If you go to download, you could see the Python 3 version. Now the latest version is 3.10.5. If you download, if you click this, you will get an exe file. Okay, it's a very simple and straightforward. The moment you double click that exe file, it will ask you next. Maybe just less than a minute, it will get installed. So with the basic Python itself, you can start writing the code using a notepad, but it has no limited features. It is not so user friendly. So what people started using is, they started using a different integrated development environment, IDEs. So there are so many integrated development environment. Now I will tell you the popular integrated development environments are Jupyter. Jupyter is the topmost in the industry. 70 to 80% of the industry people, they use a Jupyter platform to write their coding, followed by Spider editor, PyCharm, and rest of the things occupies, I will say 20 to 30%. The other IDEs occupies 20 to 30%. But majority people uses Jupyter because it has lots of facility, interfacing,
ಇದೇ ಈ
and
ಮೈಕ್ರೋಸಾಫ್ಟ್
other aspects. Okay. So this is one tool. Okay. This is one. This is standalone implementation. For the standalone implementation, you need a basic Python, followed by you have to download any of these IDE. So all these IDEs are wrapped up in a package called Anaconda. So once you, after downloading Python, then you have to go to Anaconda web page. Okay, Anaconda for Python 3, if you type, it will take you to the Anaconda distribution page. So here you can go to the Anaconda. Directly you can download this on a download page. You can see, you can download this Anaconda. Once you, after downloading Anaconda, you can able to open the Jupyter notebook page. You can start doing the coding. This is one way of installing Python and writing the code. This is standalone. Another option, what I'm going to use is a cloud-based. Cloud-based means I'm not going to utilize my laptop or my desktop resources, either my hard disk or RAM space or my CPU or GPU space. So computing, okay, this is the memory and this is the computing. I'm going to use my remote server. There are 3 popular remote servers are popular in the industry. Google, competitors, in fact, they are competitors. Google, it's GCP. We call it as a Google Cloud Server, followed by Amazon, AWS, Amazon, and Microsoft Azure. These are the 3 popular cloud-based service provider. All 3 servers are available in free. If you are a beginner, your first time you are going to write the coding, the basic machine learning algorithms, the free version is more than enough. Unless otherwise, I don't do any kind of very complicated image-based deep learning applications and all. Very large volume of text-based applications, very sophisticated algorithms. Unless otherwise, I'm not doing such a very sophisticated algorithms, deep learning algorithm, basic level machine learning algorithm. This free version is more than enough. But once you move forward, once you're comfortable working with Python codes for building a machine learning algorithms, the next level you wanted to enter into the deep learning and other high volume data when you start working with big data and all, probably this free version will hang. So you have to go with the paid version. We call it as a pro version. So basically, I go to the organizations where I teach from the simple basic machine learning till the deep learning algorithms with the real life data set, large volume data set. Obviously, the free versions I cannot manage. So I'll be working with the pro version. So I am going to use, out of the 3 cloud-based server, I'm going to use the Google Colab. Okay, how to use this open a Colab editor is very simple and straightforward. All of you have a free version. Just you log in your Google Drive. If you have a Google Drive, everybody, whoever having a Gmail account, you are able to access your Google Drive, right? Once you open the Google Drive, you have to just go for, click this new, more option. Okay, here I have a Google Collaboratory, you could see. Okay, Google Collaboratory. For the first time users, you don't have this Google Collaboratory. What you have to do is click this plus sign, connect more apps. The moment you click that plus sign, something like your Android device, your Play Store in your mobile phone, right? Suppose new app you wanted to download. What do? You go to the Play Store and you search for that app and you download it. Same as that. You just go here and search for Collaboratory. Moment I type Collaboratory, it will pop up, and all you need to do is just select and click install. It is just take 10 to 20 seconds, not more than that. 20 seconds it will install. For me, it's already installed. So that is why it shows installed with a tick sign. Okay. And also, once you installed, now you go and click this new, go to the more option. Collaboratory is available. You can click it. Once you click this, your Jupyter editor will open. The beauty here is this editor is going to run virtually, remotely in the remote server, Google server, not in your local machine. So your editor looks like this. We have so many libraries to import to work with the data. For example, some of the popular libraries are numerical Python. NumPy package is imported with some alias abbreviation, brief abbreviation, something like NumPy is being abbreviated as NP. Import pandas as PD to handle your data frame, tabular data. Last two lines, this is mainly for plotting purpose. This percentage matplotlib inline, because this is a Jupyter editor is something an inline editor. So I was mentioning about other editors like Spider and a few other editors. That editors are compartmentalized. Something like you have for coding you have one space separately, and for plotting and display you have a separate. Your entire screen is divided like this, compartmentalized like this. Spider and other editors, they are not non-inline editors. So basically you write the code here. Once you run the code, your output will be displayed here. For example, if you print a particular array, you wanted to see the result, that array will be printed here. Or a matrix, when you print a matrix, your matrix will be printed. You can see all the results here. What are the variables you have declared? All the variables will be available here. And here you can see all the plots and all. But your Jupyter is an inline editor. Okay, you write the code here. Immediately you can see the display here. You can print everything here. So everything below the cell. So your entire Jupyter is something like a compartmentalized like a cell. Each cell you can write a certain piece of code. You can run and immediately you can see the result. Another cell you can write another piece of code. You can see the result immediately. Thereby, we don't write the entire code in one single cell. Imagine if you have 100 lines of code, don't write 100 lines of code in one single cell. Because when you run the cell, it is very difficult to debug. So how do we write the coding in Jupyter cell? We divide the whole coding into many logical steps. First, you load all the libraries here. Next cell, load the data. Next cell, you pre-process the data. Next cell, you visualize you do the exploratory analysis. Next cell, you do the model building. Next cell, you do the validation. So it will be easy for you to debug and investigate the whole code. Cell by cell, we can divide the whole code and the whole code looks very neat and clean. See, you can run the cell like this. As soon as you run the cell, here you can see it is connecting to the server. It will allocate some RAM and hard disk space to us. I just show you how you can define a simple array like this. For example, I wanted to define an array np.array. Say I wanted to define a body mass index as an array. So 12.5, 8.7, 15.6, 6.2, 7.5, 15.4, 18.6, 5.7. Assume this is one array. I'm calling this as a BMI array. Okay, another array, I'm going to define blood glucose. np.array. Just quickly, I just show you the basic syntax of Python, then you'll jump into the real data. Okay. Just 5 minutes, we'll understand some basic syntaxes in Python. So for each and every BMI, I have a respective glucose value. So say this is the 200 milligrams. This is 140 milligrams. For 15.6, I have got 220 milligrams. 6.2, I have got 120 milligrams. 7.5, I may have 135.6 milligrams. 16.4, a higher BMI. Maybe I'll take 240 milligrams. Then 280 milligrams. And 118.6. Can check 1, 2, 3, 4, 5, 6, 7, 8 records. 1, 2, 3, 4, 5, 6, 7, 8. I have defined two array. So using matplotlib library, you can do a simple plot like this. PLT or you can do a line plot, plt.plot, axis BMI, y axis GLU, okay, with some symbol like, because it is a, each point is a discrete point, right? You can see my x-axis is my BMI and y-axis is glucose. As the BMI increases, glucose is also increases. Then we can decorate this X label, Y label, title, all these decorations we can give to this. Assume quickly, I just wanted to randomly take one intercept for this. Let me write one equation, y pred equivalent to, okay, my intercept is something like 100 plus 1.8 times BMI. This is a randomly selected slope and intercept. Assume this is a randomly selected slope and intercept. For the randomly selected slope and intercept, I would like to see how the line run across the data point, plot, BMI, comma, this y pred. See here, this second line is I'm going to draw as a line plot. Okay. Since I have paused the symbol, it is being plot as a scatter plot. Can you see for the randomly selected slope and intercept, it is a very badly fit line. Now I would like to see how my model predicts the glucose value, predicted glucose. These are the predicted glucose. What are the actual glucose? Actual glucose are available in GLU, right? For the first record, the actual is, for example, this is one. Where is this? This point. Let me consider this point. This is this blue point. It's around the 124, right? You can see. Sorry, that is 120. Okay, this blue data point is 120. 120 is actual. Can you see what is the orange line predicted for that? It is under predict, right? 120 is wrongly predicted as 111.16. Sorry, in fact, that is not 120, that is 118.6. Okay, still that is this blue is 118.6. The next blue is 120 actually. The second blue slightly above this, right? This is 118.6 is predicted as 110.26. This 120 is predicted as 111.16. What about this third blue? This is somewhere between 125 and 150, around the 130 something, close to this. 140, right? Okay, 140 or 135.6. Sorry, this is 135.6. This is 140. So 135.6 is actual, but what is the predicted? Predicted is under predict once again. So all the values are under predict. What is the residue? Actual glucose minus y pred is the residue, isn't it? Can you see the residues? All the residues are, all the values are above the plane. If it is all the data points are above the plane, you'll get a positive residue because your y cap is smaller value, under predicted value. So y minus y cap, you end up with a positive value. What is the condition for a good regressor model, best fit regressor model? The sum of the residues will come closer to 0, isn't it? So np.sum of GLU minus y pred. GLU is actual y and y cap. This is y pred is nothing but y cap. Look at this, 490. So it's violates. It's not a good fit. So if I use the gradient descent algorithm, the gradient descent is going to find the best slope and intercept for this. From sklearn, all the machine learning libraries come from scikit-learn library package sklearn.linear model, import linear regressor. So since I'm going to use a built-in function, this package linear regressor, it is going to estimate the best slope and intercept for us. So I have to prepare the data according to the package requirement. Okay, here I have defined this as a one-dimensional array, right? My model will not accept as a one-dimensional array. Let me show you how to define my linear regressor model. As I define a linear regressor. A model has defined like this because you have imported the library, then you call the library, you have defined the library. I have defined my model here. Now I have to fit my model, lr.fit. What is my x? My x is in BMI. What is my y? My y is in the GLU. When I run this, it will show me an error. And you see, my x has to be passed like a 2D array, because in real life, we don't single feature, right? Mostly your data frame will be like more than one feature. Like your real data looks like this. For example, I wanted to predict the sales from these three independent variables, TV, radio, newspaper. Okay, this is some sales data about a particular product. And these are all the marketing budget, how much money they have spent for the advertisements. TV commercial, radio, and newspaper, their budget. So they are in the lakhs, 230 lakhs, 37.8 lakhs, 69.2 lakhs. Sales figure in crores, 22.1 crore. So how do I define x here? It is a 3-column x, right? So the default x has to be defined as a 2-dimensional. So I have to prepare my x according to the requirement of data frame format. I have to represent my BMI. Or Panda series. So a data frame is typically, this is what the data frame structure. Okay, if you have a single column, we have something called series structure, pd.series. So once you define x as a series, now it will have some structure, which is the acceptable structure. Okay, this is a standard structure. Your scikit-learn library can accept this. Now I define x, because the x is what the properly defined structured BMI column. Y, no, there is no issues. You can keep it as it is, or even you can define your y also. Let me define my y also. Let me define as my series, my GLU. So x and y I have defined. So here let me pass x and y. So x has to be defined as a 2-dimensional strictly. Y can be a 1D or 2D. Okay, here I can make a comment. Can be strictly as data frame. That means a 2-dimensional format. Y can be defined either as 1D or 2D. Actually, 2D in the sense what? Single column data frame. That is the meaning of it. See, once I convert it to data frame, it is considered as a single column data frame. So x is defined like this. Now it successfully ran. Now once you fit your data, now you can ask what is the intercept you have learned from the data? What is the best intercept you have learned from the data? What is the best slope you have learned from the data? You can ask the slope. Slope is stored in a variable called coefficient. Randomly, we have used 100 and some 1.8 something. You can see model has learned this as the best intercept and slope using the gradient descent algorithm what you have studied. So inside this function, actually it works. Full batch gradient descent algorithm is written inside this package. Okay, now you can write your model equation y pred. I call this is the best. What is my model equation? LR dot intercept, whatever the intercept value returned by the package, plus slope. Slope comes from this coefficient times multiplied by your x, right? This is your y pred best. Let me print my y pred best. You can compare the earlier y pred. Earlier y pred we have did for some randomly allocated slope and intercept. What is the first value model predicted? 195. Okay. What is the actual stored in glucose? This is actual y, right? What is the actual blood glucose? 200. With a randomly selected slope and intercept, model predict 122.5 milligrams, but the best fit line predicts 195.10 milligrams. The actual is 200. 195.10 is pretty closer to 200. Similarly, the second is 140. Our best fit line predicts 149.06, but the randomly selected the slope and intercept predicts 115. It's a very poor score. Now we wanted to cross check how the residues looks now. The actual glucose GLU minus predicted glucose is stored in y pred best, right? Y minus y cap. Okay, because the mismatch, the data type mismatch. So I'll take y minus, okay, y pred best. Anyhow, you can take, because it works like a treat like a data frame structure, it works. So we don't have any other values for the computation here. You just simply leave it with the NAND. Otherwise, to avoid this, this is your y pred best. Okay, equivalent to np dot array of y pred best. So your y pred best is being stored as an array format. Once you present it like an array format, okay, now it can you see the y pred best is being stored as a data frame format, that we put it like a array format like this. Okay, this looks better. Now your GLU minus your y pred best in array format you have converted. This is the residues. Okay, np dot sum of the residues. Hope you remember earlier we have got a huge positive values. Can you see 1.27 into 10 to the power minus 13? This is almost zero. Almost zero. Earlier, the sum of the residues what we have got for the randomly selected slope and intercept is a huge. It's why. So this is a condition for the best fit line. Your sum of the residues is almost zero. Now I wanted to visualize this. Okay, let us visualize this. To visualize this, let me copy paste this line. Okay, let me delete this. Let me put it here. Here. So already we have plotted this y pred, right? Over the same plot, VMI, but this time your y pred best array. Can you see? This is the orange line is the randomly selected slope and intercept, and this green line is the best fit line generated by your linear regressor model. Actually, you can also compare the mean square error for this. So wherever you have got, this is sum of the residues, right? If you wanted to compute MSE and RMSE score, okay, what I can do, NP dot mean of this difference. Let me show you step by step. Let me show you step by step. So this is nothing but y minus y cap, isn't it? This y minus y cap, I square these values. Once I square this value, this is the sum of, this is the squares of the residues. Now next step, what I need to do, sum of the residues. Sum of the squares of the residues. If you wanted to know the sum of the squares of the residues, np dot sum of them. This is the sum of the squares of the residues. If I whole divided by total records, I will get mean square error. This is my mean square error. For this mean square error, if I take a square root for this, now 7.33 is the root mean square error. I was mentioning, right, just before the break, one question was there, right, why we prefer RMSE score, mean square error, rather than the absolute score is. Assume that all the glucose values are given in milligrams per deciliter. How you can talk to the client is, our model predicts the blood glucose level. Okay, some of the records it may correctly predict, like the data points fall on the line. Some data points my model over predicts. Okay, some data points my model under predicts. But our model predicts the blood glucose with the average difference of 7.33 milligrams per deciliter, which is the average difference. So what we have computed here, this is a root mean square error. RMSE, root mean square error. Okay, this is an exercise just as a giving you first exposure to Python for those people who are first time Python users. Okay, now I'll take you to some real life problem. Okay, how to work with some real data set. So this time I'm going to load some external file into the Python notebook, isn't it? So earlier previous exercise, we simulated some data. Randomly I have given this data I just randomly given. Okay, simulated data. Now we wanted to work on some real data which is there in a Excel spreadsheet. So this file is available in this path. The name of the file is advertising1.csv. Okay, in order to read some external file into the Google Colab, first of all, I need to mount my drive. Please understand, this notebook is a virtual notebook. It is virtual. It is not my standalone Jupyter notebook. Okay, this step is not needed when you are working on the standalone package. Whenever you do a standalone installation, I told you, right, Python install, then Anaconda install, then you open the Jupyter through Anaconda. You don't need to do this step. But here I have to mount my Google Drive. So I have to give an authentication permission to access my files available in whichever the account you wanted to access. You have to give the permission. So I'm giving the file permission access. Okay, allow access to access this, to read this file. So this is the, I told you, branding cost in lakhs and the sales figure in crores. So it is successfully mounted. The moment it got successfully mounted, using pd.read_csv, I have to specify the path. Up to all of us, this path is common to everybody. Content/drive, my drive, up to this step is common to everybody. Okay, inside this, I have created one folder called Regressor Models Mahesh Anand. Inside that, advertising1.csv. Okay, I'll talk about this later on. Okay, without this, let me load this first. To see the head of the data, okay, the head means it will show first 5 records. Similarly, if you display tail, it will show the last 5 records, head and tail. Totally, we have 200 records. You know that Python index starts with 0. That's why it's end with 199. Totally, we have 200 records. Okay, can you see some column called something unnamed column? Okay, if I don't want to use anything, this is a useless column. It's serial number. Okay, so what I say index call equal to 0, what I'm saying, the 0th column, I'm telling my Python function to use as a row index. Okay. So this is my row index 1, 2, 3, 4, and tail. All your records are numbered as a conventional numbers, first record to 200th record. Okay, using your row index, you can easily access the record. For example, dat of square bracket, okay, 15th record if you wanted to access. Okay, this is my 15th record. Dat location 15th index. Okay, I will show you head first to 20 records. I print first to 20 records. Can you see the 15th index? This is the 15th index. Okay, TV, radio, newspaper, sales. So 15th index 204, 32, 46, 19, right? 204, 32, 46, 19. That record alone it will access. You can access the record using the index number. So suppose if any particular column alone, if you wanted to see, for example, I wanted to see the TV or sales column. Okay, I wanted to see the sales column. That of sales, you have to use the header with quotes. Header is sales. Okay, either single quotes and double quotes is equivalently treated in Python. Doesn't matter whether you use this is the whole sales. If you put a describe, dot describe, it is going to give a 5-point summary. You know, what is the mean sales figure? The average sales is 14 crores with minimum sales figure of 1.6 crore with a maximum sales figure of 27 crores with the mean sales figure 14 crores. 50% is a median. Median figure is 12.9. And this is the first quartile. This is the third quartile. Your first quartile is nothing but your median point of between the minimum and the Q2, and your third quartile is nothing the median of your Q2 and max value. So complete summary about whichever the column you wanted to investigate, you can use describe function to get the summary. So we have another display function. One package is a matplotlib I have imported. Already I have shown this matplotlib. Another interesting plotting function is called Seaborn package. Okay, using Seaborn package, generally I prefer the Seaborn package to have a density plot. SNS dot called dist plot. I wanted to see sales distribution of sales. What is the distribution of the sales? You see the sales distribution. Whatever the 5-point summary, you can see the mean is around 14.02. Okay, mean is around 14.2. So this is the distribution of the sales figure. So similarly, we wanted to see the distribution of the money invested on the television TV budget. So TV budget is given in lakhs, all the values. You wanted to see the distribution of the television distribution. Okay.
Sir, screen is not visible, sir.
Oh. Now only, or how long it was not visible?
Hardly 2 minutes, sir, 1 to 2 minutes. That's fine.
I was worried it was too long. Yeah, no problem. Yeah. So instead of seeing one by one, you have something called a pair plot. You can investigate all features at one place. The entire data frame I have passed here. Okay. You can see all features, how it correlated with each other. You can see here, what is our dependent variable? Our dependent variable is sales. How sales correlated with the TV investment? See, as the money invested on the TV increases, my sales also increases. It's a positive correlation. As the money invested on the radio, my sales increase. This is also positively correlated. But newspaper is not does not have a very strong pattern. Okay, maybe the correlation score, maybe for the TV and radio we have some decent score, But for the newspaper, the correlation is not so strong. So how to investigate the correlation score is very simple and straightforward. Your dat.cor, CORR. It is going to give you a correlation matrix. And you see the sales is very strongly correlated to the TV. I told you from the pattern itself. The magnitude is around 0.78. And radio not bad, 0.57. But newspaper is 0.22. Anything below 0.5 we consider is not a strong correlation. It's a relatively weak correlation. Okay, so the first two features are strongly correlated, but the third feature is not strongly correlated. Looks like most likely this feature may not be eligible for the linear model. How do I prove this statistically? I need to prove and eliminate this guy, right? Because being a linear model, I need the statistical evidence to say that newspaper is not a statistically significant feature. So one way of implementing your linear regressor model come from scikit-learn library. I have imported this. If you wanted to know the statistical significance of the features, I have to use another library called, from the stats model, I have imported stats model library, which is SM library, which I have imported in the top. I'll show you. This is the library. Okay, one through linear regressor library, which come from stats sklearn package. Another one is a stats model package, SM. See, both package is going to calculate the same slope and intercept, but the only thing is my stats model package additionally gives the model summary. sklearn version will not give the complete summary. So for that purpose, I am using the SM package stats model library to use the OLS library, ordinary least square package, to implement the linear regressor. So as usual, you have to define X and Y. So I define what is my X variable, independent variable, newspaper, TV, and radio are the independent variable. My sales is my dependent variable. So I have added one more extra line to indicate that, see, by default, this OLS package will construct slope only model, Y equal to mx. It will consider the intercept as 0. I have to explicitly tell, please don't construct a slope only model. It is a slope intercept model. So how do you communicate that to the Python? You have to tell sm.add constant x. Okay, as soon as I do this, it will add a constant column 1, which indicates that now my model will create a slope intercept model. Okay, this is mandatory only for stats model library. Whereas for the linear regressor library, okay, you don't need to explicitly tell that, because the linear regressor library, by automatically it will construct slope intercept model like this. Because we have seen no intercept and slope. Whereas the OLS package, for OLS package, we have to explicitly tell that please do slope intercept model. It is not a slope only model. So for that purpose, I'm adding this line sm.add constant. Okay, so how to use that package sm.ols y comma. Okay, I have updated my capital X with this constant term I have added here, which is the indication that the model has to create a slope intercept model. Now you can see the model summary. What is the slope we got? Sorry, intercept. Intercept is 2.93 is the intercept. Look at the slope for TV and radio. The slope for TV and radio is 0.04, and radio it is 0.18. Look at the slope of newspaper. Already we guessed that newspaper is poorly correlated from the score, okay, which is scattered. And the model gives the slope is almost close to 0. Look at the slope, 0.001. This is not a significant slope. This is a statistical p-value. I was talking about the p-value during the statistical test, whether it is a two-sample t-test or Anova or a chi-square, whatever the statistical test in the background, it check according to the nature of the variable. For the TV and radio, the p-value is less than 0.05, rejects the null hypothesis. Okay, rejects the null hypothesis. That means that feature is significant. Whereas for the newspaper, look at the p-value, null hypothesis probability is very high. Okay, what is the null hypothesis here statement here? Slope equal to 0, alternate hypothesis slope not equal to 0, right? Whereas for the TV and radio, slope is obviously not equal to 0. They are significant. That is why your p-value is the probability of null hypothesis being true is less than 5%. But look at this, the probability of null hypothesis being true is 86%. Slope equal to 0 holds good. That is why your newspaper is not a significant feature. I should not include into the model. Okay, and other details are generally we don't look at these details on day-to-day problem. Mostly people look at R square and adjusted R square and this p-value. And these scores are talking about how well your assumptions are being satisfied. Say, for example, I was talking about your residue should not have any strong autocorrelation effect. Okay, this Durbin-Watson score value coming closer to 0, which indicates that there is no autocorrelation effect. So the practical Durbin-Watson score can be somewhere between 1.8 to 2.2. Okay, so I was talking about the autocorrelation effect should not exceed above 0.3. So the statistical test called Durbin-Watson test checks whether your residue autocorrelation is there is a strong autocorrelation is there or not. Similarly, we have something called Jarque-Bera, Omnibus. These are all checking the normality of the residuals and all. You don't need to look at this table better because these normality tests do a very strict normality test. But practically, I told you we give some tolerance level. Better we can check the residue manually. Okay, manually we can check the residue. So what is my model object I have kept here is model. The name of the model for this is simple model, right? I have checked the normality test here. I'll show you. Look at this. Model.resid I collect in the residue. See, can you see it is a skewed residue? You can simply check the skewness using skew function. Negatively skewed. That means I have used the variable which is violating the linearity assumption. That is why your overall your model residue is skewed. And also your residue should be near normal distribution. Okay, this is what the residue should come close to the near normal distribution. So the second model, what I'm going to do, the second model I'm going to construct only using after dropping the newspaper. Okay, after dropping the newspaper, I'm going to construct using only initially I use newspaper, TV, and radio. Since a newspaper feature was violating the linearity assumption with a high p-value, so I'm going to drop it. Then you can construct the model only with the two features. If we construct the model only with the two features like this, TV and radio, now I see the performance of the model at constant. Now I'll call this as a model 2. You can see, so they're statistically significant. Okay, the individual features are statistically significant, but still I have to check the overall residue. It is meeting the assumptions, linearity assumptions or not. So that residue follows near normal distribution or not. So now let me quickly tell about what is R square metric here. Like root mean square error is the one metric we discussed. Okay, let us see what is R square metric. So the R square, what percentage of the variation in the dependent variable is explained by your independent variable. Okay, mathematically it is defined like this: y minus y cap the whole square, I vary from 1 to n record, suffix I, divided by summation of minus y bar the whole square, I vary from 1 to n. Higher the R square, better the model. Okay, what percentage of the variation in the y is explained by your independent variables? Explainability. For high R square, I need the whole fraction to be smaller, isn't it? If the whole fraction is small, 1 minus a small number, I'll get R square is a large. On what condition I'll get the whole fraction small? My numerator should be large. Sorry, my numerator is a small and the denominator is a large. What is the logical meaning for the numerator small? What is the numerator? Y minus y cap whole square. This is a sum square error, isn't it? Residue should be minimal. Some of the squares of the residues should be minimal. Logically, yeah, we need to have a small residue. Let us talk about the denominator. What is y minus y bar the whole square? Should be larger. The distribution of the y should be larger, because here you are going to predict the sales. The spread of sales should have a larger distribution. You should not have a very narrow distribution for the y. So as long as your y distribution is large and the residues are smaller, naturally the fraction is smaller, and 1 minus a smaller fraction gives you a large R square value. Typically, as you, for a multivariate analysis, more and more features you keep on adding, what happens? No, the reliability of this R square will go down. That is why the people, they introduce something called adjusted R square. So this adjusted R square will introduce some penalty term. Okay. So if always you check the difference between the R square and adjusted R square, there will be a small variation will be there. What actually it has done is, it has introduced a penalty term. Don't trust the actual R square. Okay, the adjusted R square, because of the irrelevant features. Suppose, see here the difference in model 2, 89.6, 89.7 and 89.6. The penalty term is very, very negligible, because, but comparatively, your earlier summary, you can see here with the three features, we cannot make much difference between R square and adjusted R square. But once you have too many independent variables, and out of 10 features, say for example, there are 4 or 5 features are not significant, you can see there is a big difference between R square and adjusted R square. For example, R square says 89%, adjusted R square maybe around 85% or 84%. That means you have used so many insignificant features into the model. But here we have a very marginal difference. But as your features increases, you can see the differences are also more, and moreover, more features should be violating the assumptions, linearity assumptions. Say out of 10 features, there are 4 features, the p-value is greater than 0.05. You can see the differences is larger. So there are 2 ways I have implemented a linear regressor model. One using sklearn library, another one using stats model library. In stats model library, you can get a complete summary whether your individual features are causing a statistical and linearity assumptions or not. Accordingly, you can choose the you can have your choice of your own features, and finally you can build your better model. Now you can see this is a bivariate model. What is the slope? Slope is 2.92. Sorry, intercept is 2. Beta naught is 2.92. My beta naught is 0.04, and the beta 1 is 0.1880. So these are my model parameters. My intercept, beta 1 and beta 2. Okay, you can consider this as a better model compared to the with the multivariate model, including newspaper. Including newspaper, statistically, it is violating the assumptions. I think, so with this, let me wrap up, quickly summarize in a couple of minutes. My intention is to tell you on what occasion you can build a linear regressor model whenever you are going to predict a continuous outcome variable. Okay, we use a regressor model. Whenever you wanted to predict the categorical output value, we'll be using a classification model. Again, your business problem will come into 2 categories, linear or non-linear. So throughout our session, we consider a linear model. The constraint for the linear model is, for a linear model should satisfy so many linearity assumptions. Whereas there is no constraint for the non-linear model. Non-linear model examples, I can use a polynomial regressor, I can use k nearest neighbor as a regressor model. Even I can use neural network as a regressor, support vector machine as a regressor, decision tree as a regressor, random forest as a regressor. These models I can use for a nonlinear problems. But imagine if you have a limitation that I have to build a linear model. See, but there is a beautiful advantage for the linear model. What is the beautiful advantage for the linear model is, some clients will ask you explainability, but nonlinear model are not explainable. Suppose you come up with a model equation, you can explain to the customer something like this. Your linear model is always explainable, whereas your nonlinear model is not explainable. So whenever your business problem requires explainability, I can go with the linear model. I come up with an equation. Say, for example, previous exercise, sales in crores. Okay, beta naught. Say, for example, beta naught is say 140 plus. So see the TV, money invested on the TV in the lakhs, radio also in the lakhs. Okay. So how you can explain the equation to the customer, the client who has given this data set to you is, so every 1 unit I investment in the TV. What is 1 unit investment? Every 1 lakh I invest, my sales increase by 0.12 crores, isn't it? That means every 10 lakh I invest, my sales increase by, you substitute 10 lakh for the TV, what will happen? 0.12 multiplied by 10, 1.2 crore increases. So what is the pattern of increase? My sales figure increases. Every 10 lakh investment on the TV advertisement, my sales figure increases by 1.2 crore. For the same 10 lakh investment on the radio, okay, it is only 0.5 crore. That means 50 lakhs. Whereas the 10 lakh investment on the TV gives me the return 1.2 crore. But the 10 lakh investment on the radio will give me the return only 50 crores. This explainability is called as the inference. You can infer the equation. What is the meaning of this 140? Even if I make a zero investment on the TV and zero investment on the radio, as an average, my sales figure will be 140 crores. So independent of your TV and radio investment. So the strength of a linear regressor model is an explainability. What is the weakness? The weakness is comparable to the nonlinear model. Comparable to the nonlinear model, your linear model having a slightly high bias error. Slightly high bias error. The accuracy, the closeness of the y cap value is, we should compromise the closeness of the y cap value for the explainability. Some application demand the closeness of the y value, where you can free to use a nonlinear model. You can have your y cap value bit closer to the actual y, but there you lose the explainability. Always we have to do the trade-off. When explainability is needed, go with the linear model, or the accuracy of the y value is needed. To closer y value I need, no matter what, however the complex model is, always you can go with a non-linear regressor model. Okay. With the summarization, I just leave it to the question answers. Feel free to ask me if you have any questions.
So thank you so much, Anand sir. Now audience, so please put your questions or ask your questions directly to Anand sir.
Dr. Anand, I have one query. Shall I?
Yeah, please.
Dr. Anand, Professor Manindra Agrawal predicted some of the coronavirus pattern in the 4th wave or in the 3rd wave.
Mm-hmm.
So what do you think that he has used the same kind of model to predict the pattern of the pandemic in 3rd or 4th wave?
Yeah, good question. Yeah, good question. See, whatever we have constructed here, y as a function of x1 feature, x2 feature, x3 feature, typically what we call in machine learning as a prediction model. Okay. Whereas some data sets or something, you have a single column time series data set. Time series. Okay, on January 1, what is how many number of cases? January 2, how many cases? January 3, how many cases? I have only one single column. Using a one single column, you can treat like a pattern, a time series pattern. During a particular month, it increases, it decreases. Okay, again, the second wave experience, this is a pattern like this. Something like a rainfall or a stock market or a daily gold price fluctuations. All these comes under a time series data set. This is a pattern. Okay, all are timestamp, January 1, January 2, like this. So using this, how can I predict the count cases is here you have constructed y, maybe your glucose is a function of height, weight, body mass index, and so on. But here all I have only the count of corona cases. Here I have to build a model something like y as a function of y itself. What do you mean by that? Y as a function of y itself means I am going to predict the number of cases tomorrow based on the past few sequences. That means y as a function of time delayed version of t minus 1, t minus 2, t minus 3, and so on for the future t plus 1. This becomes a forecast problem. This is a unique problem statement. This is something like a prediction model. So precisely I need to call this a forecast. So since I use the same column, so how single column, how I can bring it to the regressor scenario? See, this is January 1, 2nd Jan, this is 3rd Jan, 4th Jan, like this. So I have to bring a tabulation. Imagine if you wanted to use the previous 1 week data. Okay, so 7th Jan, I'm going to use it as my yt plus 1. 6th Jan record, I should use it as a yt. 5th Jan record, I should use it as a yt minus 1, so on. How many lags you wanted to use? First, you have to set the lag. The pattern repeats after every 1 month or every 2 months or every 15 days. First, you have to choose the number of lags. Once you decided the number of lags, your single column data has to be represented like this time shifted version. Okay, on 7th January, how many cases are there? You have to put that value. 6th January, 5th January, 4th January, like this. So y as a number of cases as a function of the number of cases itself. That is why this is a special case of regressor called as a auto-regressive model. Auto-regressive model. People call this as AR model. There are various flavors are there. Auto-regressive moving average, auto-regressive integrated moving average, ARMA model, ARIMA model, and all. So this also you can bring it to the regressor framework, but the only difference is today's case as a function of the previous 30 days. Today's case as a function of previous 60 days. Once you capture that pattern, because what your regressor model is going to capture for the previous 30 days coefficient, isn't it? Beta 1, beta 2, beta 3. You just plug in these coefficients for the last 30 days. What is the values? Because already you have captured the slopes, 30-day slopes you have got. Just plug in the value. Then you can forecast what is the number of cases expected tomorrow, day after tomorrow, and so on. So this is a special case of a regressor. We call it as auto-regressive as a forecast model. Hope I answered your query.
Thank you so much. Thank you so much. You have explained it in very...
My pleasure.
Thank you so much, sir.
Sir, I have a question, sir.
Yes, sir.
Sir, if I choose either classification or regression problem, suppose I designing a new model by using some learning algorithm. Suppose I can get the expected prediction output. So then I go to either increase the iteration in a model or switch over to design a new model, sir.
Okay, you are not satisfied with the performance of the model.
Yes,
either you wanted to increase the iteration or switch over to the new model.
Yes, sir.
Okay, that is the question. See, first you stick on to one thing, whether
yes,
you are building a linear solution or a non-linear solution to the problem statement. First, you have to be clear with that. Within the linear, you can experiment some 2-3 options. Within the non-linear, you can experiment with 2-3 options.
Okay, sir.
Okay. So imagine that you wanted to build a linear model, because I told you for the linear model, the convergence is very simple and straightforward. My terrain is very smooth. You will always land up with a global minima. There won't be any issue of a local trap or local minima trap and all. Imagine a situation for a non-linear model. You are constructing model 1, model 2, model 3. Okay, model 1, model 2, model 3. You see the performance of these models, because the number of iterations, everything is being controlled by the built-in functions naturally. Your job is to choose the choice of combination of the features and the choice of models. What do you have to do when you do the validations? You have to validate the model using k-fold cross-validation. You have to see the model performance. Model 1, first fold, I told you, 1 fold What is the performance? Second fold, third fold. Say this is a random forest regressor. This is a decision tree regressor. This is K-NN regressor. 3 model I'm comparing. Now
Okay.
I did a 3-fold cross validation. Check what is the mean value of this. What is the mean value of this? What is the mean value of this? Out of the 3 model, which mean is the least? Okay, that model has the least bias error. Also, you have to report the standard deviation of these 3 scores. So which model gives the least best average and best standard deviation? That means the least average as the least RMSE score. Least RMSE score means, for example, this model predicts the blood glucose with the average difference of 8.5 milligrams. Second model predicts the blood glucose with the 12.3 milligrams. Third model predicts the blood glucose with 15.4 milligrams. Obviously, I'll choose model 1 because model 1 predicts the blood glucose with the average difference of 8.5 milligrams. At the same time, I check the standard deviation, plus or minus. This model, my variance error is 2.3 milligrams. Here, the variance error is, say, for example, 5 milligrams. Here, the variance error is 4 milligrams. So my bias error also high, my variance error also high, right? But only my first model is bias error, my average is least, and also my fluctuation also within the control level. So obviously I will go with my model 1. So we have to experiment with multiple models, and finally when you do k-fold cross validation, we have to pick the best model.
Okay. Sir, another one, sir.
Yeah, please.
Suppose if I increase the iteration for, I think just I'm going to first initial for 100 iteration for some neural network models, because based on neural network models, we optimize some weight parameters for each either 100 or 200, go to 1000 or 10,000 iterations. For each iteration we can get the good parameter, like optimal weight parameters.
Yeah, correct.
So this thing will create a great like some.
Can you repeat? Your
performance
voice is
measures? Yes. Performance measures.
See, the thing is, see, for example, you are solving a nonlinear problem. Okay,
Yes,
with an input, one hidden layer, hidden layer, and output architecture. Okay. Whenever you say, for example, with 100 iterations, you run the algorithm.
Okay.
You can notice that because when you see, say, for example, I do a regressor or classification. If it is a regressor, you are every iteration is printing the RMSE score. For example, every time it prints 18.5, 18.4, 18.
It's like that.
Somewhere, but you are expecting somewhere better score around 10.3 is what your expectation.
Yes.
Okay. Even though I run this for 1000 iteration or 10,000 iteration, nothing improve means there is a flaw in my architecture. Because with a one hidden layer architecture is not able to solve this complexity. What I need to do, I have to introduce another hidden layer.
Okay.
Another hidden layer. Then you reiterate from this.
Yes.
So first you see, introduce the layer. Okay, introduce the layer and try to increase the neurons in the layer.
Yes.
Introduce each layer will try to form one decision boundary. For example, this is what my data. It's not a linearly separable. Say for example, like this. Okay, so without hidden layer, my neural network model tried to form a decision boundary like this. Definitely, it will end up with high error. It will not converge. Okay. Now what happened? No, you add one more hidden layer. When you add one more hidden layer, actually, what neural network is trying to do? Okay, adding one more hidden layer, it will try to form one more decision surface like this.
Yes.
Adding another hidden layer, it is going to form another decision surface like this. Another hidden layer, it is going to. So it is trying to form a multiple linear surfaces. Okay, it's a combination of concurrent simulation of multiple linear surface. Together, it is going to form one complex decision surface. So your neural network looks like a one complex decision surface. This is what the decision surface. Okay, this surface is, finally it is solving the problem like this. So this way you can, as an experimentation basis, you can either increase the neurons. If you increase the neurons, what will happen? With one layer, if you increase the neurons, with less number of neurons, it will form the surface very strict, straight line. As you increase the neurons, it will make the surfaces like a very soft surface like this. make the
Yes.
surfaces a very soft surfaces, smooth surfaces.
Yes.
So either by increasing the neurons or by adding an extra layer will try to solve your problem. You have to see, and every time initially don't run your algorithm with the 10,000 iteration or 1 lakh iteration. Always
Okay.
you try to see the convergence happens with 20 iterations you see. With the 20 iterations, the values keep reducing 18.5, 16.5, 14.2, 12.3, 10.6. Like this, it should converge. Instead of
Yes.
converging like this, it will get stuck 12.2, 12.1, 12. Like this means your model is underfitting. So naturally, you have to increase the layer and try to increase neurons like this.
Yes. Okay. Sir.
That way you can better tune.
Thank you, sir.
Yeah.
Any questions? Questions are most welcome from the audience. Okay, if there is no question, let me thank the business person for a wonderful lecture. Thank you very much, sir.
Yeah, my pleasure, sir. Thank you very much. Thanks for the kind invitation once again. I thank the Department of Mathematics,
Thank you very much, sir, for your nice
Professor Balasubramanian, and the coordinator, everybody. Thank you so much. So you can connect with me in LinkedIn. You can search for Mahesh Anand Great Learning. You can get my LinkedIn page. I request you can connect with me in LinkedIn. You can post your queries in LinkedIn Messenger also. I try to answer it whenever I get it.
Thank you.